Hello everyone, let's get into the next topic of today's lecture, which is about shifting instructions. So shifting is a very useful operation in C, especially if you want to do bit operations. It is also very useful in assembly, and we'll get into why it's useful later on. So there are some other nice side effects of shifting. For example, if I shift an unsigned number to the left, it is the exact same thing as multiplying by the corresponding power of 2. This is really nice because shifting is a much faster operation than multiplication. Plus, multiplication is technically not supported on all machines, though I'll get into why that is the case in a later video. One thing to note though is if I shift to the right, it is not necessarily the same thing as division, and you should do a few examples just so then you can understand why. We have different types of shifts. The first one is logical shifting. That is where we actually add zeros as we shift. We also have arithmetic shifting. So this is where we sign extend as we shift. Arithmetic shifting only really makes sense for right shifts, so there's really only a right arithmetic shift. And the most important thing is it's nice because it preserves the sign when we shift. When we shift, we can either use an immediate value or a value in a register to tell us how many bits we want to shift by. Here are the different instructions that RISC-V supports for shifting. We have the left and right logical shifts, and we also have right arithmetic shifting. Once again, the logical shifts will fill in those bits that just got shifted with zeros, as opposed to the arithmetic shift, which will fill in those bits with whatever the sign bit was. For all these operations, it only uses the lowest 5 bits, so you really should only be using the values from 0 to 31 when you're doing shift operations. So let's get into some quick Let me get into a quick example of some shifting operations you can do. So first I want to load in this hex string, which is equivalent to -256 into T0. Next I'm going to perform some operations on T0, but I'm never going to change it, so it's all going to be based off of this original value. The first thing I want to do is shift left by 3. As you can see, I have an immediate value here, which is why I have a number right here. And I've shifted this value by 3. You might be wondering, why is it 8 now with this shift? I mean, would I just shift each of those F's over by 3? Well, once again, you gotta think this is a bit operation, which means I'm going to shift bits over by 3. So I'm going to take each bit and shift it over by 3. If you're wondering how we got 8 out of this, think back to what or how many bits you need to represent F. If you thought 4, you are correct, and if you realize that you need all 4 of those to be set, you are absolutely correct as well. If you shift those 4 bits over by 3, you'll have the most significant bit being set, which is why we actually see the value 8. All the other values here are F's, because once again, all these values here, or all these bits here, were all 1, which means we're just going to transfer them over, and that's why these are still all set. Next, we have a right logical shift, and we're going to shift this by 8 bits, or 1 byte. And as you can see here, we have 2 nibbles, which is equal to a byte. We've just essentially moved all these F's over here. Once again, since this is a logical shift, we filled in the upper bits with zeros, which is different from an arithmetic shift, which is also shifting by the same amount, where we sign extend. And the most significant bit in this case was a 1, because once again, F is all bits set. So the most significant bit here was a 1, so we're going to sign extend that, and that's why we have all F's when we perform this shift operation. I finally want to give you a quick example of how RISC-V actually only really uses the lowest 5 bits. So let's say I load in the value -22, that's equivalent to this little hex string, and let's extract the lowest 5 bits, so we have FFFFFFEA. So once you pay the microtransaction, you'll be able to figure out what the lowest 5 bits are, which is just 0, 1, 0, 1, 0. And finally, let's perform a shift operation. So the shift operation, this is a shift left logical once again, is going to shift by 10 in this case, because that is what these bits are equivalent to. So this operation here, this adding in the shift left logical, is equivalent to a shift left logical immediate, where I shift by 10. So next I want to get into some fun instructions. So the first one I want to go into here is, how could I implement load byte unsigned if my machine never actually supported load byte unsigned, but it supported load word? So the first thing, let me just give you an example. I wanted to get out the first byte of whatever the address in S0 is and store it to S1. So the first thing I want to do is I just want to load in the entire word, because I need to get the data regardless, and load word is the only load operation I claim that I have on this machine, so let's just get all that data. Next, I'm going to load in a bit mask. I'm using the pseudo instruction load immediate, which essentially will take or we'll split this into multiple different instructions if needed, so that it can fill in, or so then it can create the bit mask that we need to actually get the second byte here. And that's what this AND is doing. It's taking this bit mask and ANDing it with this, so then we can get the second byte here, which is what is equivalent to 1 when we're doing a load byte unsigned. Finally, we have a shift right logical, and that's going to shift this right to, or this is going to shift it right by 8, so then we actually fill these bits into the lowest thing right here. Do note that this is not a signed operation. Once again, this is a logical shift. And anyway, if I'm using the second bit right here, I can't actually sign extend because the most significant bit is a 0 because I've set these to 0. If you wanted to do a signed load byte, you'd have to do a little bit more witchcraft to actually get it to work, and I'll leave that as an exercise for you guys to try to do. Going on to this ridiculousness, let me say that my machine does not support store byte, but I want to implement store byte. Say I only have store word, similar to how I only had load word in the other machine. So the first step is, well, I want to figure out what is the store byte operation I want to do. In this case, I want to store to the third byte, or the most significant byte essentially, of this address, this value right here. So the first step is I want to get out the entire word of data, because I need to change the value in that before I store it back. So I've just loaded this value in with this load word. Next, I create this bit mask, which is load immediate, and then I AND it with the entire word there. The bit mask that I created actually sets the upper bits to 0, which will allow me to actually OR it together with the value that I want to store in there. So as you can see right here, I've shifted whatever I want to store to the left by 24 bits, so it's in the highest location, so that when I OR these together, I will take whatever I just got here, or whatever I got here, as in each bit, I'm going to take this or this, and I'm going to merge those together essentially. The reason why this works is, once again, I did an AND operation, which means all these bits are going to be the original bits, minus the upper byte essentially, so the upper 8 bits. And then when I do this OR operation, that means I'm going to have these as zeros, and then for this operation right here, I'm going to say that T1 has all zeros for the least significant bits, which will allow this OR operation to combine those two values without changing those two values. Finally, I've actually changed the value that should be stored back into memory, so then I'll use a store word with that new value I've created. Once again, there are some ways how to make this much more general, and I would recommend that you actually try to do that yourself, because it is a very fun, different method of actually trying to create different instructions with a fewer subset of instructions.